Hi, my name is Peter Karkus, and I will talk about our ongoing work on visual navigation using differentiable robot algorithms, which we submitted to the Gibson and Habitat challenges. This is our navigation system running in simulation and in the real world. While we watch this, I want to give credit to the challenge organizers for putting all this amazing infrastructure together, and thank them for inviting me to speak here. I will first talk about our work on differentiable robot algorithms, and then their application to visual navigation. The majority of robots today are built based on the principle of modularity. A robot system is composed from models and algorithms. I'm using models in the classic sense, a dynamics model or a friction model. And then algorithms, for example, for perception, state estimation, planning, and control. These robot systems are composable, but they're often brittle because of inherent approximations and modeling errors. In response, the modern end-to-end approach directly optimizes for the task objective using deep neural networks. It produces powerful but highly specialized systems that lack strong priors, meaning that they need large amounts of data to generalize. We would like to reconcile the conflict between the two sides and combine the modularity principle with robustness to end-to-end learning. Differentiable algorithm networks, DANs, provide a principal framework for composing robot learning systems. DAN has modular structure. It separates models and algorithms, but it's trained end-to-end, just like a neural network. The key to do this is to think of both models and algorithms as part of a single differentiable computation graph. This computation graph is a generalized neural network that includes both learnable parameters as well as fixed operations that implement an algorithm, for example, a planner. Because everything is differentiable, we can backpropagate gradients through the algorithm and train our models end-to-end. In the past few years, differentiable implementations of many classic robot algorithms were developed for state estimation, planning, and control. We also showed that these modules can be composed together in the context of visual navigation. We had experiments in procedurally generated 3D environments like this and obtained some interesting results. Dan performed much better than a standard neural network because the algorithmic structure it encodes is a strong prior for learning, just like how convolution is a strong prior for image processing. Dan also performed much better than standard modular systems, even though both use the exact same structure with the same algorithms. The difference is that in the standard systems, models are trained independently, each optimized to be accurate in general. In contrast, Dan trains all models together to be useful in the context of the task, rather than to be accurate in general. We found that such task-oriented learning can compensate even strong approximations in various interesting ways. If you want to find out more about DANs or these results, you can visit my website or check out the paper below. In ongoing work, we aim to use the idea of DANs for visual navigation, eventually in the real world. The objective is for a robot to navigate in previously unseen environments to given goal coordinates using only first-person visual observations. Navigation has been studied for a long time in robotics. The typical pipeline starts with a module for mapping and localization, or SLAM, that iteratively constructs a global map and estimates the robot pose on the map. The map is fed to a path planner that finds the path to a goal. And finally, a controller tracks the path, outputting model commands to the robot. In principle, all these components could be treated as DANs, and we can train them all end-to-end. Instead, we chose to only apply DAN to the SLAM component and use a standard ASAP algorithm for path planning and a simple PID controller for control. We made this choice because planning and control, at least for our robot platform, are very well-studied problems. The remaining challenge is to extract spatial information from visual input such that it integrates well with the downstream planning and control. Existing SLAM solutions may not produce maps that are easy to plan with. They might not work well in the presence of moving objects or with the low video frame rate that we have in the domain. Our differentiable SLAM module encodes fast SLAM, a classic SLAM algorithm based on particle filtering. Now, this is how the architecture looks like. First, we predict a local top-down map from first-person visual input using a CNN. The local maps are accumulated into a global map by using appropriate image transformations and the predicted robot pose. The SLAM algorithm maintains a set of weighted particles for different hypotheses of all past poses. So each particle consists of a hypothetical trajectory, a sequence of past map predictions, and the weight that measures how likely the hypothesis is. At each time step, the trajectories are extended with samples from a dynamics model. The particle weights are updated with a learned observation model that intuitively measures the compatibility of the trajectory with past observations. This observation model is the most important component of the architecture. It estimates the log probability of the latest local map given the current pose hypothesis and all past local maps and poses. We approximate this by a sum of pairwise compatibility estimates of the current map pose pair and the past map pose pair. This compatibility measure is learned by a CNN, where the input is a concatenation of the current local map and the past local map, or where the past map is transformed into the current map's viewpoint based on their relative poses in the hypothetical trajectory. We use the same CNN weights for each pairwise compatibility estimate, and we repeat it for all k particles, updating eventually each of the particle weights. The pose estimate is given by the weighted sum of the pose hypotheses. We also resample particles, so over time, unlikely trajectories are drawn. The differentiable SLAM module on the high level is just a computation graph that encodes a particle SLAM algorithm and its learned models. We train it in a supervised manner to predict a correct robot pose and a traversability map, where a cell is free if the robot can move there without collisions. We trained a network with the shortest path trajectories from the habitat simulator and evaluated based on the final pose estimation error at the goal. When just unrolling the dynamics model, the pose error is under our threshold 18% of the trials. With the differentiable SLAM network, we got 50% success with only 32 particles and 66% with more particles. We also tried the SLAM module in the full navigation pipeline. While this work is not finished by any means, we submitted it at its current stage to both the Habitat and Gibson challenges and obtained some promising results. In Habitat, the actions are discrete, so we did not need the controller module, but otherwise we used the rest of the architecture as discussed before. So we achieved about 48% success on a local validation set. While the challenge outcome was not known at the time of this recording, but the performance was comparable to the public leaderboard. Looking at our failure cases, roughly half can be attributed to not reaching the goal in time, and the other half for accumulating too large of a pose estimation error. Moving on to the Gibson challenge, here the robot location is directly observed, so we only use the mapping component of our differentiable SLAM approach. The challenge features 3 different scenarios, as shown here: static, interactive, and dynamic. The only strategy we used for these scenarios was to leverage our task-oriented setup so that our mapper learned to distinguish interactive objects from obstacles and did not add them to the map. So this is an example of our agent navigating in a previously unseen environment. In simulation, we obtain 62 to 66% success on our validation set. When the robot succeeds, it's typically also close to the optimal path. Looking at our failure cases, significant number of trials involved collisions with objects very near the initial state, which are very hard to avoid. Rest of the failures were either collisions or not reaching the goal in the time. So as part of the competition, the policy was also executed on a real robot platform in a real world apartment. Somewhat to our surprise, the first time the policy was executed on the robot, it solved 30 to 40% of the trials. And it also ranked first in the leaderboard for the development split. The final evaluation round involving harder trials, we got ranked second in the best performance in the interactive scenarios. Our Sim2Real transfer was our strategy was merely to use depth-only input, so the visual reality gap was small. What caused most of our failures was a significant actuation delay, for which our control parameters were poorly calibrated. In many cases, our policy was trying to do the right thing, but the robot wobbled a lot and eventually making it too slow to reach the goal in time. So maybe one message here is that interpretable models make it much easier to debug and fix this kind of issues compared to, let's say, a monolithic neural network. Having now identified an issue with the control delay, we could probably fix the problem having access to a similar robot, or we could even swap out our controller to one shipped with the robot's ROS package. So in conclusion, we believe that scaling embodied intelligence will need the right combination of structure and learning. DANs provide a framework that encodes the structure of algorithmic computation and their connected models in a single computation graph and trains them in a task-oriented manner. We showed some promising early-stage results on visual navigation, performing close to the best in 2 navigation challenges. Thank you for watching, and feel free to reach out with any questions or comments. Thank you.